Thanks, Armin. Yeah. Hello, everyone. I'm Jian Hao Zhang, from a research scientist from University of Colorado and Boulder and NOAA Chemical Science Laboratory. I'm working with Graham Feingold. And also I want to thank Brian for the discussion on the RSP data. So we already seen very detailed macrophysical studies from the Activate team, and we think that our contribution could be the ability to zoom out a little bit and focus on some of the emergent properties of this complex aerosol-cloud-meteorology interactions over the Activate region. So what do I mean by emergent properties? So first, I want to introduce the silico path and D space that you have seen already. Just the previous talk has focused on this. So the reason that we chose this geophysical variable space is that even though we focus on the macro physical properties, we can infer some process level understanding. For example, in this phase diagram, we can highlight some directions that we think are consistent with our physical understanding of the cloud system. For example, droplet activation, if you go along with this arrow following the same effective radius ISO line, you see this droplet activation process, and then this condensational growth direction, and direction the collision coalescence, where you have droplets collecting into bigger droplets, and then you see a decrease in number with a fixed liquid path. And on the other hand, you have entrainment processes, which can be seen both homogeneous and inhomogeneous mixing, where you have a fixed number, where you shift the size distribution, or you have smaller droplets evaporating faster, and you see a decrease in droplet number. And another phase space is this albedo cloud fraction phase space. This is for all clouds derived from satellite observations. You see this non-linear increase of albedo with cloud fraction. However, if you break down into different morphology, you see a more linear relationship in the closed cell stratocumulus cases compared to other morphologies. And also, you can see the similar stuff in from our larger ID simulation outputs. Another phase diagram I want to show is this cloud albedo liquid path relationship. So here I'm showing this diagram, but with some data from our large ID simulation ensemble of stratocumulus region. So one thing I want to highlight is this cloud breakup. You can see this is color indicating the cloud fraction. So higher cloud fraction, and we have two pathways of cloud breaking up into open cells. The first one is through this entrainment pathway, where you kind of keep the same number concentration so basically you can indicate a number concentration in this diagram from fixing the liquid path, varying the albedo. That will be your macrophysical response of albedo because you have the same liquid path. So this will be the entrainment breakup, and then you have the precipitation breakup, where you have a decrease in number and increase in droplet sizes and lowering cloud fraction. And this is just showing in the simulations, you see this cloud water path to liquid path ratio really drops in this precipitation region. So the first thing I want to show using some Activate science is this coda outbreak evolution. So this is all from a GOES 16 satellites, liquid path, number concentration, and albedo. So the goal I'm trying to retrieve here is to see the evolution of the cloud strait. So I coded this kind of 2D trajectory model just to use the surface wind to advect air masses along this strait to capture this evolution. And so here I released, this is about 20 trajectories, and then you see the mean of evolution in liquid path ND space and cloud albedo and liquid path space. So the thinner lines indicates individual trajectories, and the solid line, the thicker line is the mean among these trajectories. So the first thing is, I think this represents a typical precipitation-driven breakup, where this is nicely showing up here. You have in this direction, you have a droplet activation phase and condensational growth phase, and then the coalescence collision coalescence really get you to larger droplets and lower number concentration. You see this on this day and also on this day as well. So this is the developing phase, and then you have this breakup phase. So then if you look at the satellite imagery, this is GOES optical depth retrievals, and then you can kind of already see this different phase of the evolution. So developing phase, and then this really thick clouds with high number concentration, and they start to break up into precipitating cells, open cells. And then there's on this day interesting reactivation or condensational growth in this phase, in this region, and then another breakup. Just to show you that there's a lot of process level understanding we can learn from this liquid pulse ND space. And on the albedo side, it's just this is your developing phase, and then when you break up, because of the droplets is larger and you have less droplets, the albedo is much reduced when you're in this breakup phase. It's showing up pretty nicely in both cases. So there's also days where you encounter this entrainment breakup mechanisms where you have a really strong activation phase, and then because in this case the liquid pulse is not that high, and you have lots of droplets, and this gives you a condition where entrainment is enhanced, and then you kind of follow the same trajectory, the same evolution as you as in the development phase as you break up. So we don't see the precipitation breakup in this case, and we see some of the collision coalescence in this case because of the liquid pulse is really high in this case. But still, it's not enough to really kick in the strong precipitation to give you the open cell structures. Because of this, we see similar cloud albedo when you break up for this entrainment-driven cases. So, so the idea is to introduce this phase diagram, and we have lots of, from Paquita's group, we have detailed in situ measurements looking at these cold air outbreak cases, and we also have the modeling groups also looking at this. So I want to initiate some collaboration that we can put all the in situ modeling and this is satellite on the same phase diagram to see some if we can better understand what's going on within different approaches. So another thing I look at is this. This has already been talked about a lot during this morning. The liquid pulse ND relationship for the activate region, which is really interesting. When I first starting to look at this activate data, this is what I showed last year, and Stella also showed this this morning. A global map of liquid pulse ND relationship is this inverted V. And if you look at the stratocumulus region, Northeast Pacific is nicely showing up this inverted V from satellite. For activate region, we really see this this positive correlation, a high number concentration. At first, I thought this is just due to the cold air outbreak cases, because I just show you, you have this strong developing phase of a positive correlation between liquid pulse and D. If you include these cases in your analysis, you can just get a positive slope. So one thing I'm trying to understand is this some confounding factors we are missing. For example, in the stratocumulus regions, we don't really have this dynamic environment where we have a strong gradient in aerosol, and we have also the Gulf Stream doing is giving you the buoyancy fluxes. So first thing I want to test is to get rid of those cold air outbreak cases and see if we can still see this inverted V. So this is from non-cold air outbreak cases for all 3 years of data, RSP-derived liquid pulse ND. So if you just look at this, this histogram of liquid pulse ND, and this is the column mean, column median, you see the inverted V to a point, and then even without cold air outbreaks, you still have this little tail of positive correlation. So I want to understand what's going on over there, and then I composed the data by the cloud-based turbulence. So this is a measure of the below cloud legs, the vertical velocity in the below cloud legs, and then I composite the slope of liquid path ND as a function of this updraft or below cloud turbulence. And you can see that at high turbulence conditions, you do see this positive correlations. And I'm trying to just use this to explain that we see this high anomaly concentration conditions, we have this positive correlation. But still, this is ongoing. We still need to look into individual cases to make sure this is the right way to interpret. However, I want to point out a cautionary note on this. So if we do some co-location comparison between in situ number concentration, in situ effective radius, and RSP effective radius and satellite effective radius. This is showing a different approach, giving you the retrieving the same variable but with different degree of uncertainty. So this is how in situ compare with RSP polarimetry, RE. You see this there's a positive bias in RSP, and when I put RSP as X function and modus, the bispectral retrievals, you see this modus overestimate RSP. So the modus is the furthest away from the in situ. So, and then this is the RSP derived liquid path ND relationship, and this is modus derived. You see so much, there's a remarkable difference between the two the two relationships, and there might be trying to figure out if this is possible without any physics, just due to a retrieval bias from satellite methodology can give you something like bias like this. So Paquita recently pointed me to this paper where they kind of investigate this this bias or retrieval bias of in effective radius that can possibly give you an inverted V, even though the data was synthetic data was initialized with a positive correlation between liquid path and ND. Just by adding effective radius arrow, you get this right line. So this is your inverted V without any signs, without any physical signs, just by arrows. And so this is some possibility that we can look into in the future with activate data, because we have this co-location of two aircrafts and a satellite above. So to summarize, so the cold air outbreak cases, we want to get some collaboration going for this maybe intercomparison. And I want to look, next step is to understand some large scale control, for example, SST on this precipitation versus entrainment driven breakup. And then, yeah, and then characterize this liquid path ND relationship and see if there's anything we can learn from the activate that speak to this uncertainty in RE, and how much does it cause the inverted V shape we see in satellite. And last but not least, I want to say that we know that people tend to use this inverted V to infer aerosol cloud interactions. It works quite well in stratocumulus regions. Can we really generalize that to all low clouds is the question. So I think Activate shows one example of conditions that we cannot really infer aerosol cloud interactions without knowing other things going on in this region. Yeah, that's it. Thanks for your attention.
Thank you for very interesting results. My question is, when you talk about different relations based on the ghost data, I mean, overall, ghost data are not too bad, but those relations are not from measurements, are essentially a model parameterization during the retrieval. And the question is, can we even trust those relations in the parameterization for the ghost retrieval compared with even models?
Yes. So You mean this right here, right?
Yeah, or
Okay.
to the beginning, you talk about from the ghosts. I mean, essentially, those are not from measurements.
Are you talking about the Kodak outbreak cases or
Right. Yeah, yeah, to
Okay.
the beginning.
Yes, so I think those are pretty robust features because Kodak outbreaks is very unique. The liquid path ND, the reason that you see this loops and then consistent with our physical understanding is kind of a validation of how good GOES is, right? You can put satellite or institute data over there, but I think the physics is go at least GOES is getting the right physics in terms of those evolution in Kodak outbreaks. That's my interpretation.
Okay. My point is relation has nothing to do with the satellite measurements. That's from the parameterization in the retrieval. The measurements are fine, but they do not measure the relation between different quantities.
Yes, I agree with you. Yes, yes.
Very interesting presentation. I think Ghost is great. I don't have the results here, but I will share with people. But I'm curious about your comparison between MODIS and RSP. So I'm assuming the cloud rubber number concentration from RSP is derived from um, cloud effective radius and optical depth.
Yes.
So that means that similar uncertainties could happen also in the RSP.
Right.
So the question is not here whether we can trust satellite retrievers or not, or whether we can trust cloud Doppler number concentration derived from remote sensors, right?
So yeah. So in this region, is the real problem is the adiabatic assumption is really appropriate to use here. So the reason that I didn't show ND comparison is just because the adiabatic fraction is such a variable in this region, and but I think RE effective radius retrievals is comparable. We can at least this is below cloud top lags, and yeah, but yeah. Yeah.
Yeah, there's a paper by Michael Witter, which is pretty nice, that finds almost no bias it's looking at effective radius. So we have to walk back from droplet concentration because that's more challenging because of the adiabaticity. But the effective radius is essentially not biased high. It's partly the probes, and they claim that the PD, this phase Doppler one gives you more realistic. You want to talk about that?
Yeah, I'm familiar with that paper. We have used a number of observations, and the data that so far I like the most is the RSP particle size. It's not only because Brian is here, but it's because and has shown us a great comparison um, and again when we compare and the RSP against MODIS or other geostationary satellites for different field campaigns, for oracles, names, activate, to name a few, we still obtain positive bias in the satellite cloud effective radius. So I think it's real. And I think Michael's paper is interesting, but it's a very narrow data set because it's mostly focused on the stratocumulus cloud region. So particle sizes don't change that much over there. So I'm almost very confident that this bias is real, unfortunately. But on the other hand, optical depth is underestimated. So that's a good thing, because when you compute cloud number concentration, you have an overestimated effective radius and underestimation in cloud optical depth. And surprisingly, that gives you sometimes an unbiased cloud number concentration.
But it's important when you're talking about MODIS's droplet size to say which band you're using, because they're not all created equal. So, we've got pretty good agreement quite frequently with both Modus and also with David Severi and GO's 3.7 micron droplet effective radii. That is simply not the case for 2.1 or 1.6, and especially not for anywhere where there are cold air outbreaks or low sun angles.
Okay, Gao, you're cutting into the break. No, we'll restart at 3. However long this takes, our break is till 3.
It's all my fault. I'm sorry. So while do the in situ effective radius, how much do you average the data?
So in situ, it's lag, lag average.
Okay, so it's like an hour.
30 minutes.
Okay, sorry, got it.
I'm not sure about the exact minutes of, but less than an hour, I guess.
3 minutes?